All right, thank you. So I'm going to report our work on the carbon sequestration of type 1 and type 1L cement with the addition of the nano-silica. So in the morning, our colleague He has reported some preliminary result on like mechanical test result with the addition of nano-silica. So now I'm going to talk about the carbonation performance of type 1, type 1L cement with the addition of nano-silica. So here is my report contents with 5 parts. So firstly is the research background and the motivation. So we all know that cement industry has a very high carbon footprint, right? So if you go to EPA website, it will give you the carbon dioxide emission calculation result for different industry. So we can look at the cement production industry. We can see in 2021, the cement industry emitted about 70 million metric tons of carbon dioxide. So we all know the cement industry usually emit about 8% of the carbon dioxide for the global cement emission. So last month I participated in another conference. There's a researcher from PCA. He said we are devil. We emitted a lot of carbon dioxide to our beautiful planet, right? So we want to reduce the carbon dioxide emission to our beautiful planet. So they said, okay, let's try to use type 1L cement, because according to the PCA, they said type 1L cement compared with Portland cement, OPC, it has same durability, it has same resilience, and it will reduce up to 10% of carbon dioxide footprint, right? So if we consider another perspective for the concrete industry, so the production of cement will emit a lot of carbon dioxide, but after hydration, the hydration product, calcium hydroxide, will carbonate. So this process will reabsorb the carbon dioxide from the air, right? So this process called the carbonation process, so which means the concrete has the sponge effect to absorb the carbon dioxide. So according to this research in 2020 in the Nature Communication, it says for the future reabsorption of carbon dioxide will be significant because we have so many concrete structures, right? But the climate goal compliant net carbon dioxide emission reduction along with the global cement cycle will require both radical technology advancement and the widespread deployment of the material efficiency measurement. So now because I come from Purdue, Purdue is in Indiana. In Indiana, we do not have OPC, we only have PLC. So I tested some carbonation process of the type 1L cement, because in the cement production process, we already reduced the carbon dioxide emission because we use some limestone to replace the clinker, right? But how about the next step? How about the carbonation process? Will the PLC absorb enough carbon dioxide? So firstly, we characterize the cement. So we obtain the type 1 and type 1L cement from the Booz Unison. The cement plant is in Greencastle in Indiana. So we can see the type 1L cement has a slightly finer particles compared with type 1 cement. And the density for the type 1L cement also a little bit lower than the type 1 cement. Usually for the type 1 cement or OPC, we know the density is about 3.15 grams per cubic centimeter, but for type 1L cement, the density is lower than 3.1 grams per cubic centimeter. And we use the TGA to look at the TGA curve for the raw cement. So we can see the type 1L cement did have more mass loss in the temperature range from 550 Celsius degree to 725 Celsius degree, but this difference is not very much. The type 1 cement has about 7.32% of mass loss in this range, and type 1L cement has about 10.23. So the TGA result tells me there's not too much difference, but still type 1 cement did has a little bit more of the carbon dioxide, right? And we look at the meal certificate. And we compared the meal certificate with our XRF results. So there's not much difference. So we just report the meal certificate result in here. So we can see from the meal certificate report, there's not too much difference in terms of the chemical composition for type 1 and type 1L cement. The biggest difference is the aluminum content. Type 1 cement has more aluminum, but the type 1L cement has more magnesium. And if we look at the loss of equation, we can see type 1L cement has almost 2 times of the LOI result compared with the type 1 cement. And the limestone cement, type 1L cement is reported to have about 11% addition of the limestone, but type 1 cement only has about 4.32% of limestone in the cement. And the blend fineness is consistent with the particle size characterization result. The type 1L cement particle is finer than the type 1 cement. All right, so we also added Nano-silica into the cement paste. So this Nano-silica is a colloidal Nano-silica. It has about 70% of the liquid and 30% of the solid. So for this 30% of the solid, we use XRF to characterize that. So it has about 98% of the silica dioxide and about 1.5% of sodium. Others is about 0.14%. So the density is a little bit higher than the water, 1.2 gram per cubic centimeter. So under the TEM image, we can see the particle size of the Nano-silica is about 10 to 20 nanometers. So it's real some nanomaterial, right? So this is a test program. So firstly, we mixed the OPC and the POC cement paste. So here 3 and 6 means the dosage for the Nano-silica. 3 means 0.3 weight mass ratio of the cement for the Nano-silica. So remember, for 0.3, there's only 30% is Nano-silica, another 30% is liquid, right? So very, very small amount of the Nano-silica added into the cement paste. So firstly, the water to cement ratio is 0.45. We cure it at 23 Celsius degree for 28 days. After 28 days, we use some experimental method to characterize those POC and OPC with different amount of Nano-silica, and then we put these cement paste cubes into the carbonation chamber. We have a pressure port, so we inject the pure carbon dioxide into the pressure port. The pressure is 50 psi. So we carbonize those cement paste until 28 days. After 28 days, we take the sample out. We grind the sample from surface to interlayer for 7 layers, because we know the carbonation happens from very surface area, then the carbon dioxide will penetrate into the cement paste. So if you want to compare like the TGA result for different carbonation sample, it's very hard to control the carbonized degree, because sometimes you may take from the very surface area, sometimes you may take some from the intersurface area. So some people may control the result, right? So we want to compare the carbonation degree for different samples very precisely. So we grind the sample into 7 layers. So test the TGA pH value for every layer. So I'm going to report the result later. So first is the hydration property of the cement paste with the addition of Nano-silica. So we can see first is this image shows isothermal calorimetry result. It seems the POC release more heat in first 7 days of isothermal calorimetry test than the OPC, because POC has finer particles, right? It will react faster. Another thing is we can see, very interesting, with the addition of Nano-silica, the hydration heat is reduced for the first 7 days, because we have reported in the morning, the Nano-silica will form the silica gel. So this silica gel will resist the water evaporation. So if it resists the water evaporation, it will also resist the water transportation inside the cement paste. So in first 7 days age, the hydration heat is lower. But at 28 days, if we look at the TGA result, the chemical bond water and the hydration degree both improved with the addition of Nano-silica, and the chemical bond water for the type 1L cement is higher than the type 1 cement paste. And then it's the carbon dioxide uptake. Firstly, we recorded the mass change for those cement paste cubes in the carbonation chamber. So we can see the OPC showed a higher mass improvement compared with PLC, because PLC, it has about 10%, 11% of the limestone, so it actually has less cement clinker. So obviously it will absorb less carbon dioxide, right, in the carbonation chamber. But with the addition of Nano-silica, it improved a little bit of the carbon dioxide absorption if we use the mass change. So we can see from the TGA result for the cement paste at 28 days, we can see with the addition of Nano-silica, it has more calcium hydroxide. So that's why with the addition of Nano-silica, it will show higher mass increasement, right? And then we use the TGA test to look at the carbon dioxide uptake for every layer of the sample, from surface layer to the inside layer. So we can see most of the carbonation absorption most of the carbon dioxide was absorbed by this very first layer. So we green the sample in every 2 milliliters. So we use the average value. For example, 1 milliliter means the first layer, and the 3 milliliter means the second layer. So we can see the calcium hydroxide content improved from the surface layer to inside layer, and the calcium carbonate decreased from surface layer to the inside layer. So after carbonation, cubes were grounded into 7 layers, and the TGA and the pH value test was performed on each layer. So we can see then we calculate the carbon dioxide uptake from the TGA result for the calcium carbonate calculation result. So we can see the the carbon dioxide uptake result showed a very good correlation with the mass change measurement result, right? So with more mass improvement, it will uptake more carbon dioxide. So we can see for the OPC6 means we added 0.6% of the Nano-silica into the OPC sample, so it absorbed most of the carbon dioxide. But for the PLC, without any Nano-silica addition, it showed just very small amount of carbon dioxide absorption. And then we used the MIP measurement to look at the microstructure. So for the MIP, after 28 days of the curing in the saturated lime water, we cut the sample into like about 5 milliliter particles. We prepared about 10 particles for every sample, and we took 5 samples to do the MIP without any carbonation, and we put another 5 samples into the carbonation chamber. And after 28 days of carbonation, we taste the MIP result for those carbonized samples. So we compared the microstructure change before and after carbonation. We can see very interesting things. The PLC sample showed higher porosity, and with the addition of the Nano-silica, the porosity is slightly improved. And after carbonation, the porosity reduced. And if we look at the pore size distribution, we find although with the addition of Nano-silica, the porosity improved, but the pore size is finer compared with those samples without any Nano-silica addition. So we can say although the addition of Nano-silica improved the porosity of those cement paste, but most of the improvement is the fine pores, smaller than the 20 nanometer. In the next page. So here shows the pore size distribution before and after carbonation. So after carbonation, we observed the porosity was reduced, right? So most of the reduction for the porosity is for those pores finer than 20 nanometer. And the porosity reduction also showed a pretty good relationship with the mass change improvement result. And next page, we used the micro-CT to look at the real pore structure of those cement paste samples before and after. So here is the sample before the carbonation, and here is the sample after the carbonation. So the before and after carbonation is exactly the same sample. So we drilled the cement paste sample with about 0.45 inches with the diameter and about 1 inch length. So we use micro-CT to characterize pore structure before and after carbonation. So first thing is with the addition of nano-silica, we can see there's less pores observed in those cement paste samples, so which is consistent with the MIP result. There's less large pores with the addition of nano-silica. Most of the improvement in the porosity is the small pores. The small pores cannot be characterized by the micro-CT because for this test, the resolution is 18 micrometer. And another thing is after carbonation, we can see the porosity did reduced. There's less pores observed in the micro-CT result, and here is the POC result, also consistent with the MIP result. And then we also measure the pH value for different layers of sample. I have introduced how we measure the pH value in the morning. I would like to reintroduce it. So we green the sample for every layer. So we have 7 layers, right? Then we sieve those cement paste powders into 150 micrometers. So we got very fine powders. So we mix these very fine powders with DI water, and then we shake it. We use magnetic stir to shake it for 2 days, and we store those samples in the vacuum. So make sure it will not be carbonized in the air, right? And after 2 days, we filter those suspension with 0.45 micrometer filter. So we got those liquids. So we use a pH meter to measure the pH value of the sample. So we can see the surface layer showed a very low pH value. Then we go to the inside layer. The pH value increased because the carbonation degree is reduced for the inside layer, right? But the pH value showed a very good correlation with the calcium hydroxide content result from the TGA result. And another thing is with the same amount of calcium hydroxide content in this image, with the same amount of calcium hydroxide content, the OPC showed a higher pH value. So maybe the OPC is good for like durability because it has a higher pH value, but the POC did absorb less carbon dioxide. So maybe from another perspective, POC is also good for the durability study. So we have more work to do, right, in the future. Yeah. So the basic conclusion for this study: adding nano-silica may result in reduced hydration heat at first 7 days, but the 28 days results showed nano-silica will improve the hydration degree, and due to the reduced clinker content, the carbon dioxide uptake efficiency of the type 1L cement or the PLC is lower than the type 1 cement or the OPC cement paste. So in this testing, the adding nano-silica will improve the carbon dioxide uptake efficiency of the cement paste. The reason could be the improved calcium hydroxide content and more transportation channel because the porosity improved, right? And the modification of CSH gel with the incorporation of nano-silica and this effect on carbon sequestration will be explored in the future study because I only have 15 minutes. I have finished the test, but I cannot show it today. I hope to show it in the future. Thank you.